the discussion will be on hypothesis testing. And from onset, we made it clear that it's not just learning about R. R can be used for many tasks. You can use it to perform many tasks. But I think the main objective of PiLAF is to build capacity in data analysis. And that's what we have tailored this training towards. For today, hypothesis testing is the focus. And generally, hypothesis testing is done when you are dealing with sample or when you have performed an experiment. You are trying to test, or you have a claim, or you have a hypothetical value, or you have assumption that you want to establish. So we learn how to go about hypothesis testing in this lecture. So hopefully you should be able to check some fundamental assumptions, particularly regarding normality of your data. You should be able to look at your data, detect outliers. You should be able to perform univariate tests, maybe one sample t-test and proportion test or binomial test, chi-square test for goodness of fit, and of course for association. And yes, we will not be going to independent tests. I think that's we are not going to do two-way or whatever. So, but we are focusing on univariate tests. So the content of the lecture will be on first giving us a background to hypothesis testing, and then we also provide a short background to normality assumptions and how we can detect outliers. We will now go to the RStudio and demonstrate the application of whatever we provide, that background that we provide. Then we come back here and I will introduce you to univariate test, one sample, t-test, and then we'll go back and demonstrate in RStudio. Then we'll come back. So we'll be going back and front until we finish this. So we have quite a lot. So our hands are full tonight, and I need your cooperation. So when it comes to hypothesis testing, there are basic steps that you must get right. So it all starts from you gathering your data, and then you formulate the hypothesis. Though ideally, this is when you are testing, but when you are actually doing research, the flow will have to start from the conceptual framework, and you have to also specify the hypothesis you are testing before you now collect data. But the presentation here assumes that you already have the data, and then you can formulate the hypothesis, and then you choose appropriate test statistic, and then you calculate this test statistic. So once you calculate, you now come to the decision region, and here you have to decide whether you should reject the null hypothesis or whether you should not reject it. And if you reject it, it means you conclude that the alternative is true, which means it's significant, the test is significant. And if you do not reject the null, you conclude that the null might be true. And in that case, the test is not significant. And generally, in hypothesis testing, you might have two categories of tests. You can have two-sided test, like what you have here, or one-sided or one-tailed test. So if you have two-sided, then it is a test in which the alternative is not given any direction. So here you have the alternative saying the null is saying mu equals to 23. The alternative is saying it's not equals to 23. So it's not directional. It's not saying whether it's lower or higher. So in that situation, it is two-tailed. So generally, if you want to decide whether a test is two-tailed or not, it is the alternative that we indicate. Look at the one-tailed. So if you look at it, the null is saying it is greater or equals to 23, and the alternative is saying it's less than 23. So this is a left-sided hypothesis. So it's left-sided because of the direction of the alternative, not because of the direction of the null. Similarly, this is the right tail. So it's right tail because of the direction of the alternative. And so what you should know about hypothesis testing is that it divides your decision region into two mutually exclusive parts. So one part belongs to the null, the other part belongs to the alternative, and they can never intersect. So they are completely mutually exclusive. So we will talk about this when we demonstrate, talk more about it when we demonstrate shortly. And the final part of hypothesis testing is to take decision. So we have decision group. I'm proud to your even data collection or whatever, you must have chosen the level of significance. The level of significance is usually the probability that you will reject a correct hypothesis. So that probability is usually very small, and that's called type 1 error. So once you have chosen your level of significance, ideally it should be before you even collect the data. But I've seen many people, so once they have seen the result, they start struggling, which one should I choose? So it's like you looking at the goalpost carefully before you kick your ball. So the next thing is to obtain the p-value, and that is obtained, the computer will give you the p-value, calculate it from the value of the test statistics. So you compare the p-value with the alpha value that you have chosen. So you reject the null hypothesis if the p-value is smaller than the alpha value, then the test is statistically significant. On the other hand, if it is the p-value that is greater than alpha, then the test is not statistically significant. In that case, you are not able to reject the null hypothesis. So the first test that we will carry out is normality, test for normality. And why is it important? It's important because many of the statistical tests available, developed, they rely heavily on this assumption. And if the assumption fails, then the test may no longer be reliable. So, and that's why you need to check if the assumption holds. So most tests, which are called parametric tests, they rely on distributional assumption, particularly normality assumption. So some statistical techniques that rely on this assumption include t-tests, which assume that the sample data is normally distributed. The two sample t-tests also assume that either both samples, sample A and sample B, are normally distributed. ANOVA, which is analysis of variance, has underlying assumption that the residuals from the model are normally distributed. Even the regression, particularly the normal linear regression, assumes that the residual from the model are normally distributed. So most of these, all the techniques I've mentioned here and many others have the underlying assumption that the technique, make the assumption that the data we are dealing with are normally distributed. So in checking for normality in R particularly, we can use two methods. We can use the visual method and a formal statistical test approach. So for this lecture, we will use both visual method and statistical test approach. For visual method, we can use histogram and Q plot, contact plot. If the histogram shows or the shape looks like a bell, or we say it's bell shaped, then the data will be assumed to be normally distributed, and I will show you. If you plot the Q plot, contact plot, and the points in the plot, if all the points roughly fall along a straight line, with straight diagonal line, then the data will be considered to be normally distributed. So in the case of formal statistical tests, we can use there are over 100 statistical tests for normality in literature, quite many. So, but often most of them will give you the same result. So, but for our demonstration, we will use Shapiro-Wilk test and then the Capybara test. So we simply look at the p-value of that test, and if the p-value of the test is greater than the alpha, then we say the test, the data is normally distributed. Same thing with Capybara. Once the p-value is greater than the alpha, then of course we cannot reject the null hypothesis, and therefore we accept that the data is normally distributed. But often we can reject the null hypothesis and find out that the test is significant, which means the data is not normally distributed. And if that happens, then you need to transform the data. So that's not the end of the road. So you can use log transformation, take the logarithm of the values and continue. Or you take the square root of the data, all the values, and check again. Or take the cube root. There are different transformation techniques, but these are just some of them. So now we go to RStudio and demonstrate that. So this is the RStudio. So of course you should know where your folder is, your working folder. So the first thing you might want to do is to click open and look for where your file is located. My working folder is my text desktop, and this is PiLAF, and then I look for the file. This is the hypothesis test file. Yes. So you click it and then you open. So this is the script file.
It's not working, sir.
The first thing we want to do is not working. Thank you very much. Did I get it right? It's not working. Did you say it's not, or it is working? Hello. Okay, so the first thing you'd like to do is to set your own working directory, because if you run line 4, it will not work for you. That is my own working directory. So to do your own, you go to session, you go to set working directory, you choose directory, and then locate where you have saved where your working folder is. This is my own. So I now say open. Then you will now copy whatever you see here and paste it on my own. Paste it on top, override this one, and you are good to go. So you will be able to, I believe you have in that folder the demographics.csv data file. So you can now read it. We use this data in my last class, and even last week it was also used. So this is the data, and you can look at the data set. It actually has information about car owners. It has 8 variables and information about 510 car owners. The first person, age 55, married, income 72, education, did not complete high school, car price is this, car category is luxury, gender is female, retired, no, still active. So that's about the data. And if you click here, you can see the variables and the type of data that you have. And of course, we can also run line 6 to look at the internal structure of the data. So this is the internal structure of the data. So that is a real life data. But because of what I plan to do shortly, we can also simulate a data that will be normally distributed, because the data, the numeric data here, like age, income, and car price, they are not normally distributed. So for you to have idea of how a normally distributed data looks like, so we are going to simulate one. So I'm going to set a seed in line 9. I set a seed. This seed, if you have the same seed, it will help you to reproduce the same data that I am going to simulate. But if you change the seed, we will not be having the same data. No, it will still be normal, but it will not be the same data. So I run line 9, set the seed. Now I can draw my normal variable from a random normal distribution. So that's what this function will help us to do. So I'm going to draw 2000 normal data. So I will name it normal data. That's the variable name. So I run this, and of course, immediately you will see the data here. You have 1 to 2000. If you want to see the internal structure of the data, you can see. So this is the first one. If you want to see the head, you can see the first. Yes, this is the first 6 values, and these are the last 6 values as well. So for the head and the tail. Now, the first thing we want to do, remember in my preamble, in my background, I said we could detect normality in data series by visual method and by statistical test. So we are starting with visual method. So I'm going to create 2 by 2 rows and column, 2 rows and 2 columns. So that I will draw the histogram. So draw the histogram of the normal data, this one. So I run this. It's working. So this is the, I have to do it again. I didn't partition it. So I'm going to run this, and I'm going to now, yes. So this is for the histogram. And then the second one is going to be the histogram of income here. Income is the variable in the demo data. So I'm going to produce, this is its own histogram. And you can see the shape of the normal. You can see the shape of the skewed. You can see, I will still talk more about that. Then we can use contact plot also to see whether the data is normal. So first, I run this for the normal data, and then produce the contact line. So the line is there now, and then for the income, I produce this and the contact line. So let's look at these plots here. So you can see the shape of a normal data. So if the histogram is like this, then the data is normally distributed. You look at the tail on this left side and the tail on this right side, they behave the same way. And it's possible to even fold this at the middle here so that this one will lap this one will lap this one will lap this one will lap this, and so on. When your histogram is like this, then it is normally distributed. But look at this income, in which there is no tail even at the left-hand side, but the tail at the right-hand side is very long. So this type is said to be skewed, and is skewed to the right. So this type of data is not normal. So you can also look at the QQ plot here. So the ideal thing is to have majority of the points lie on the, the straight line. Even though we have few that are slightly not on the line, but yet you have quite long number of majority lie on the line. So the behavior you see here is reflecting the behavior here. The behavior you see here is reflecting the behavior here. So we can conclude here that this is normal. So this is called the theoretical context. But if you look at this, look at serious departure here. So you can see this is not normal, because you can see quite a large number of the observations are not on the straight line, both at the tail and at the upper part. So the essence of this plot is for you to see how a normal data looks like, a normally distributed data looks like, and how a non-normally distributed data looks like. So that's much about using visual approach to detect normality. What about using formal tests? So we are going to use Shapiro test. So for Shapiro test, you simply need to use this function Shapiro.test, and then put the data here, the variable here. So you can run this, and then you see the result. This is the p-value. So remember the rule. The rule says if the p-value is greater than alpha value, that's when you should accept the null hypothesis. So in that case, you cannot reject the null hypothesis. So our p-value here is greater than alpha value. So we cannot reject the null hypothesis. And therefore, the test is normally distributed. Yes, I can. Is anybody raising up hand? None. Good. So as far as Shapiro test is concerned, the test is normally distributed because the p-value is greater than alpha value. Maybe our alpha value at 0.05. Doesn't even matter which alpha value we choose. So, yes. Puka, what's the problem?
I I can't plot my own histogram.
I know why you cannot do that. So what happened probably is try to expand this place and make it a bit bigger.
Okay, sir. Thank you, sir.
If it works, let me know. Does it work? Okay, well, we wait to hear from you. Let's now go
No, sir.
for the... Huh?
No, it's not working.
It doesn't work. Bigger margin too large. Did you follow? Is anybody also getting the same problem?
Yes, sir.
No. What's the error message? What's the error message?
I think it's from the demographic survey. I don't have it here.
Demographic data. If you don't have it, but the command here, did you run the simulation I asked you to run? Yes, okay, you are okay now. Yeah, that's good. So that's good. So I'm happy to hear that. If there's any other one, let me know. If there's any other problem, please try to follow. Then, so for us to use Dakubera, we need to load this package. So you need to check. If you don't have it, that is T series, you might need to install it. So install it. But if you already have it, then simply run line 34. But if you don't have it in the packages, go to install and then type T series and install. So I have it, so I can just require load it, and that will, once it's loaded now, I'll be able to perform the Dakubera test. Still loading. It's a bit slow. I know it's there. T series. So it's loading. Yeah. So it has been loaded. So we can run. I can run this Dakubera. This is the function that you use. Daku.bera.test. So you can now put the variable name there. So again, this is the p-value, which is 0.5867. And since this p-value is greater than 0.05, so we cannot reject the null hypothesis. The null hypothesis is one that claims the data is normally distributed. The alternative is the one that claims the data is not normally distributed. So with this p-value, which is much higher than the alpha value, we cannot reject our null hypothesis. And therefore, this data is normally distributed. So that's how to check for normality, whether using virtual approach or using the statistical test approach. Now we move to the issue of outliers. So outliers are usually values which you can consider to be unusual when compared to the rest. They are not consistent with the remaining observations. That doesn't mean they are not legitimate. Sometimes they could be legitimate, but sometimes they could be due to extraneous factors, such as when you have contaminated data samples, data points from different populations, incorrect sampling techniques that you have used, underlying significant treatment response, e.g. if you have a biological variation of samples, or if you have error in data collection, or even in the data entry, data processing, that will also lead to outliers. So just like the normality test, you could use the visual approach. There are three visual approaches that are mentioned here: histogram, scatter plots. We just used these two. So in addition, we have the box plot, and I explained this very well in my last class. This is box plot. So values that are below this expected maximum, they are outliers. Values that are above this expected maximum, that is Q3 plus 1.5 times the interquartile range, they are outliers. Values that are below the expected minimum, they are outliers. Expected minimum is computed using this formula, Q1 minus 1.5 times I, interquartile range. This is interquartile range, which is simply Q3 minus Q1. This region is Q2, or the median. So, but once you have the box plot, you just look for whether you have values above the expected maximum or values below the expected minimum. We could also detect outliers using formal statistical tests. These are three popular tests: Dixon's Q test, Grubb's test, and Rosner's test. So these tests can be used. They have their limitations, which I will show you shortly. So let's now demonstrate this in the R studio. So now we want to detect outliers in data series with the help of visualizations. So first of all, I'm going to also partition the plot area into one row, three columns. So so that I will have histogram in one, box plot in the other column, and then the QQ plot in the third column. So let me run line 41, and if you are following me, you can also run that. Is anybody raising up hand? Yes, Timothy. Can you share? Okay. So let me continue. That's good. So I run line 41, which partitions the plot area into three columns of one row. Then I run line 42, which produce the histogram, and then line 44, which produce the box plot, and line 44, which produce the QQ plot, and then draw the QQ line, which will be a line like that. So let's discuss these plots. So these are the plot. This is histogram. Normally, how can we detect outliers here? Is a bit difficult to detect outliers in this histogram. But if you compare this with the case of income, you will see outliers there. If you look at, yes, this one, let me zoom it also. You can see, whereas you have the concentration here. As a matter of fact, there are 510 observations in the demographics data. 400 are honey, below 100, and then about 100 are honey below 200, making 500. So only just about out of 510, just a little below 500, and below 200, and then you can see maybe one or two isolated cases, honey, about 900, about 1,000 plus, and 100. So these are people who are honey heavily. They must be senators, the ministers, and so on. So here you have lecturers and teachers and people like you and me here. So you can see outliers there. Somebody is laughing. Okay, that's good. So these are outliers. Therefore, you can also detect it here. Look at this. These are very conspicuous outliers. Again, you can see few, but not so pronounced. So let me go back to the previous one. Yeah. So to this one. So you see from the box plot, these are the only outliers. Remember, in this plot, we have 2,000 observations, 2,000 observations. Yeah, so you have this, anyone that is above this line, they are outliers. This is the expected maximum, and this is the expected minimum. Anyone below, they are also outliers. So again, this QQ plot is also showing what is happening at the top here. It's also showing what is happening at the bottom here. So we can see few outliers. Even in a normally distributed, we can expect to have few outliers, just about 0.3% of the entire data set. So how then do we detect outliers using formal test, statistical test? So there is a package called outliers. If you don't have it, you can install it. Click install and type outliers, and you see suggestions. You can click and install. But I have it, so I can just upload it here. So I will upload it, and then so it's now loaded. The first statistical test we will use is Dixon's Q test. Dixon's Q test. The limitation of this is that it will work if the sample size ranges between 3 and 30. So I'm just going to take a simple example. Suppose you have scores from a mathematics test. So I call it maths, and this is the score of the first, this is the score of the second. So there are how many students there are? 1, 2, 3, 4, 5, 6, 7, 8. So we want to detect if there is outlier in this grade. So Dixon's Q test will not take anything below 3 or anything above 30. The observations must be between 3 and 30, and that's one of the most very critical limitation of this test. And another limitation is that it can only check one value at a time. It can check whether the maximum value in the data set is an outlier or not, or it can check whether the minimum value in the data set is an outlier or not. Other than that, it cannot do anything again. So let's run this. So the data is now loaded as math data, and then we can now apply the Dixon.test function to the math data. So the Dixon test for outlier says that this is the p-value, and this is the Q statistics, and this is the alternative hypothesis. The alternative hypothesis says the highest value on its own, it detected the highest value in the data to be 76. So the hypothesis says the highest value, 76, is an outlier, which means the null hypothesis is saying the highest value, 76, is not an outlier. It's not an outlier. So, but looking at our p-value again is greater than alpha. If we choose alpha to be 0.05, since p-value is greater, it means we cannot reject the null hypothesis. Remember, the null hypothesis is highest value 76 is not an outlier. So we cannot reject that null hypothesis. And then we can conclude that the highest value 76 is not an outlier. If we now want to check for the lowest value, which is 10, so we will now simply use this argument opposite and set it to be true in our function. So if I run this now, so I have the alternative to be lowest value 10 is an outlier as the alternative, which means the null will be saying lowest value 10 is not an outlier. So the p-value again is greater than 0.05. So we cannot reject the null hypothesis. So in conclusion, the lowest value is not an outlier. The highest value is not an outlier. That's for the Dixon test. So, well, later Groves came up with his own, and it can only work if the sample size is above 6 and the data is normally distributed. So we overcome the limitation that Dixon had. So if we have anything above 6 observations, it will work. If it's smaller than 6, no, Groves test may not be able to detect outlier. Yes, quick one. Okay, somebody is trying to join. Okay, so the Groves one, just like the Dixon, can check for maximum value as an outlier. So in our, now that we have our normal data, which is about 2,000 observations, so we can apply Groves test. So if I run Groves test on our normal data, then I have this result. So it detected the lowest value here to be minus 3.39 and so on. So the null will be lowest value minus 3 point so is not an outlier. The p-value is 0.06, which is also greater than 0.05. So we cannot reject the null. So we conclude that the lowest value minus 3.39 and so on is not an outlier. Then we can check again for the other side if we use the opposite argument. So this saying highest value 3.19 so is an outlier. So the null will say highest value 3 so is not an outlier. Since the p-value is exactly 1, is it greater than 0.05? So we cannot reject the null hypothesis. So in all, the lowest value and the highest value are not outliers. The last formal test is the Rosner's test. And it can detect fairly accurately up to 10 outliers when the sample size is at least 25. But the data must be normally distributed. So to do that, you need this package. You need this package mstats. So I can require this. I have it. So if you don't have it, you need to load it. So I have it. So it's loaded now, and then I can run it. So unlike Groves and Groves, this one can Dixon and Groves. This one can detect up to 10, outliers at the same time. So I'm even setting my K to be 10, so I can run this to make it fairly easy to interpret. Let me rerun it so that everything will be visible. So it takes the first observation, and this is the conclusion here. Outlier is false, is false, is false, and so on. So this is the mean, this is the standard deviation, this is the value, this is the observation number, 392, and this is the R and the lambda. Don't need all of that, but this is the final decision, which is either false or true. If it is false, it means that observation in observation number 392 is not an outlier. So this is how you use the Rosner's test. So this is exactly half this the middle of our work for tonight. Is there any quick question for me to address? If not, I like the way you also use the chat menu, please continue to use it. Thank you, team, for helping me out. Now, let's move to univariate tests. So when we talk about univariate, we are talking about techniques that summarize only one variable at a time. When we talk about bivariate, so we look at techniques dealing with two variables. Uni means one, bi means two. So in bivariate statistics, you are dealing with two variables. In multivariate statistics, you are comparing, two or more, variables, or more than two variables. So, what our concern is tests that are meant for summarizing or drawing inference on just a single variable. So these are the very common one sample t-test. You use this to determine whether or not the mean of a population is equals to an hypothetical value or a known value. So you only use it if the variable is numeric or quantitative. So you don't use this for qualitative variable. But for qualitative variable, you use binomial test. So because you'll be talking about proportion in that case. So if I'm talking about gender, so I can look at proportion of male in that population, proportion of male in that population, or proportion of the population that is infected by coronavirus or whatever. So a binomial test is meant for proportion. So if you are dealing with qualitative variables. The chi-square test also is for categorical variables. So for the goodness of it, you want to determine if data fits a particular distribution. But for the test of independence, it's not really a univariate test. In this case, you are going to be dealing with two qualitative variables. So we might be testing whether one qualitative variable is independent of another qualitative variable. For instance, we might be looking at whether the category of car, which could be either luxury, standard, or whatever, and then whether it's independent of the gender. So the two gender and category of car, they are qualitative, and then we can test whether one is independent or the other. So now we will go to our RStudio and demonstrate each of these. First is to perform a one sample t-test. And before we do that, let's look at our data again. This is our data. We have marital age is quantitative, numeric. Marital is qualitative. Income is quantitative. So in all, only three variables are quantitative. So we can only, if we are to use the t-test, it can only be applied to the quantitative ones. And if we are to use the binomial, it can only apply to the qualitative ones. So we are starting with the t-test, and we will be dealing with income. So there are assumptions which we must check. One, the variable must be normally distributed. We have discussed how we can test that, so we are not going to do that again. The variable also must not present any significant outliers. So again, we have learned how to do that. So we have checked for both normality and outliers. But what do we want to test now? We want to test whether average income of car owners in this population is significantly different from 70. So this is income of car owners. As a matter of fact, you have car owners who earn income 72, 153, 28, and as you have seen in the histogram that we drew, people earn income as much as 1,000, 1,000, yes, as much as 1,200 and some. So you have people earning high income and people majority earning low income. So, but our hypothesis, the hypothesis we are testing is whether the average income is significantly different from 70. So we will now use the t.test function, the t.test function. And there are arguments there. The first argument is to name the variable you want to use. This time, this is the variable income. That's why it's demo $income. So the next is the hypothesis that you are testing. Remember, in my initial presentation, you are looking at this hypothesis that mean is equals to a known value. So that is what we are giving. That's what we are trying to present in that code. So mu is equals to 70. That is the hypothesized value. So then another argument is alternative. And here you have to state if the test you want is two-sided or two-tailed, whether this one, so we are starting with a two-tailed, two-sided hypothesis. And then you specify the confidence level. So here it is 0.95, which of course means that the alpha is 0.05. So we can run this two-tailed test and get our results. So this is one sample t-test, and this is the result. This is the t-statistics, 1.7282. This is the degree of freedom, which is 510 minus 1. This is the p-value, which is 0.08. This is the alternative hypothesis, which says the true mean is not equal to 70. And from here, we can deduce that the null hypothesis is that true mean is equal to 70. True mean is equal to 70. That is the null hypothesis. This is our p-value and is greater than 0.05. Therefore, we cannot reject the null hypothesis. So we can now conclude that true mean is equal to 70. True mean is equal to 70. So that will be for this two-sided. The thing is that even if we reject the null, this one does not tell us the direction. That's just where the confusion will lie. If we reject the null, even though we are accepting it in this circumstance, but let's say we reject the null and we accept that the alternative may be true. It simply means that true mean is not equal to 70, but it doesn't show us the direction. It doesn't tell us whether it's greater than 70 or whether it's less than 70. So, but one left tail or right tail test will help us to know the direction. So this is the 95% confidence interval, and this is the mean of the 510 observations, which is 78.59415. Let's run a left tail hypothesis. So the only thing that will change there is this alternative, which we set to be less. So that argument will be less. And it means we are testing this hypothesis. The null is saying the average income is greater or equal to 70, and the alternative is less than 70. So let's run that, and that gives us this result. So the alternative is saying true mean is less than 70. True mean is less than 70. Again, of course, I've told you just now the null is saying true mean is greater or equal to 70. And because the p-value is greater than 0.05, it means, again, we cannot reject the null hypothesis. So the true mean is greater or equal to 70. Now let's see what the right-tail test is saying. The right-tail test is saying true mean is greater than 70. Boom. Look at our p-value. Our p-value is less than 0.05. This means we can reject the null hypothesis and therefore conclude that the alternative is true, that the true mean is greater than 70. So this is how we can easily know the direction of our claim. So that's about the t-test. Let's look at how to perform the binomial test, which is proportional. The class is not, I hope everybody is following, or am I the only one in the class?
We're following, sir.
Yes, we are.
Okay.
We are following, sir.
Okay. I thought I was teaching myself.
We are following, sir.
Okay.
So I didn't follow, sir.
Peter is not following. You will come and teach the class if you are not following.
We are following, sir.
Okay, thank you. Anybody who is not following will become the teacher, and then I will be glad to follow the person. So let's continue. I know I'm actually raising up, but I'm happy you are able to catch up. Thank you very much. This is a wonderful class. If I have money, I will give to everyone, but no, not now. How to perform the binomial test. And I told you, you can't really perform binomial test with quantitative variables. So you might, you need to be dealing with a qualitative variable. So we want to check in our case whether the male, female proportion is in the population is 50-50. So we are checking whether 50% of the car owners are male and 50% of the car owners are female. So the first thing we need to do is to create a count table of variable gender. So remember, we have, this is variable gender in our data. It's not showing here, but we can easily see it here. So this is the variable gender. So we have male, female, male, male. So there are two possible categories there. Yes. Is it that somebody is raising up? Okay, no. So there are two categories. So we have to create a count table to see how many are female, how many are male, and that's what we'll do here. Let's print the table. So there are 250 female and 260 male. So we are testing hypothesis whether female is 50% and male is, because that can confuse some of you. This 510 represents sample of car owners. So, but we want to use the sample to draw inference about the population. So we can only compute from the sample. This is what we are getting. Of course, this is not 50-50. But the purpose of this test is to draw inference about the population. So based on this sample information, we can now say the population of car owners is 50-50 male, female. But let's check. So it's always important you know which of the level is your reference. The one that you see first here in your table is one that R is taken as your reference. If you want to change it, you can change it. There are ways to change it. And we have taught you before how you can specify factor and levels. So if you specify factor for uh, for um, variables that are categorical, you can also specify the levels, the order in which the levels should be. So, but for this, female is the reference point. So always take note of that. And so if we want 50-50, we will set our proportion to be that of female, which is 0.5. So we use the binomial test function. And then my table here will be the data that will be used. And then we also test for two-sided as well as provide the confidence level. So we are good to go now. And then we run this. And this tells us, so this is the data, my table, and then number of successes. So success here refers to female. So any in the table female now, which is the reference, is considered to be success. So number of trials is 510. That is the number of observations in the data. And then this is the p-value, 0.6903. The alternative hypothesis says true probability of success is not equals to 0.5. Of course, from here, you can deduce what the null is. The null will say true probability of success is equal to 0.5. And because our p-value is greater than 0.05, we cannot reject the null hypothesis. So we can conclude now that true probability of success is equal to 0.5. So from this, we are saying the population of car owners is actually 50-50. It's actually 50-50. So this is the 95% confidence interval. And you can see within this interval lies 0.05, sorry, 0.5. So which means it's correct. And this is actually the probability of success, 0.4901, which is 250 over 510. That is the probability of success. We can do the other one, the test for, this is the right tail, and then you can, I leave you to draw your conclusion. This is the left one. I leave you to draw your conclusion. The other one, which is a bit trickish, is to check whether the proportion of male subject is 60%. So if you are not careful and you use 0.6 as your p in the script, in the function, then you will get it wrong, because this is talking about female subject as 60%. What is here, since our proportion is about proportion of successes, and success is defined as female in this case. So we have to you have to consider that. So we cannot use 0.6. Since we are asking for male subject is 60%, it means we are also asking for female subject to be 40%. So if that will be our P, 0.4 and not 0.6, because whatever will be here must be whatever is proportion of whatever is considered to be success. And female is success in this case. Even though the question is asking for male, then it has to be 1 minus the proportion of male, which will give us the proportion for female. Every other thing will work. So we can now run this. And then let's look at the results. So this one is saying true probability of success is greater than 0.4. Of course, look at the p-value, very small. The p-value is very, very small, which means we are going to reject the null hypothesis that true probability of success is less or equal to 0.4. So the alternative is accepted, and we conclude that true probability of success. In other words, probability, proportion of female, which is success, the proportion of female is greater than 0.4, is greater than 0.4. So if the proportion of female is greater than 0.4, then what do we say about the proportion of male? Can it be 60%? No. So that's how we will now answer this. So because if this is greater than 0.4, then the proportion of male cannot be 60%. Again, this is the confidence interval for 95% confidence interval for the proportion of sources. And this is, of course, this one will not change. So that's how to perform the binomial test. Just two more things to do before we conclude. I hope you are able to get that. If there is any question, no question, okay. Thank you, Tim. You are really helping me. Yeah, the demo data, yes, is in the class. It's in the Google Classroom. You can always download from there. Now, we want to talk about chi-square test for goodness of fit. So basically, when we talk about goodness of fit, we are looking at two things: the data that we have, and then the model that we fit. Does the data fit the model, or do they agree? So if they agree, then we talk of goodness of fit. But when they disagree, then there is no goodness of fit. So I'll get you to understand that better. So we in this demonstration, we are going to use the categorical variable education. And I told you, when you are dealing with binomial test and the goodness of fit, which we use chi-square test, you are using those tests only when you are dealing with qualitative, and I repeat, qualitative variables. So, or in this case, categorical variable. So the variable we are going to consider in this case is education level. Let's create the count table using this. So we are using demo educ. Educ has different levels. Did not complete high school, did not some college, and so on. But we will see it in the table right now. So I can run this, and then I can print the table. So these are 5 levels. Category: college degree, did not complete high school degree, postgraduate degree, some college. And we, out of 510 car owners, 113 of them had college degree, 125 did not complete high school, 132 had high school degree, 27 had post-undergraduate degree, and 113 had some college degree. Now, the real thing is to talk about, since we have 510, there is what we call theoretical probabilities. So, which means, in a layman, theoretically, we will expect this 510, the proportion to be equal or true, so that this 510 divided by how many groups? There are 5 groups. So 510, we expect that 102 will have college degree, 102 will have will not complete high school, 102 will have high school degree, and so on like that. That is what we call theoretical probabilities. But what we have, sorry, not probabilities yet, theoretical expectations. But this is what we call the observed values. So this is observed, this is the observed. But the 102 I mentioned represent the expected values. Represent the expected values. So in this situation, we are first of all we are interested in what's the length of the table. That is, so we represent that by n. That's how many. So of course we can print n. There are 5 of them. So this is the 5 representing college degree, high school degree, some degree, did not, and so on. So that is then the theoretical proportion. The theoretical proportion is 1 all over n, which means I expect 1/5 of the total to be in each group. So I run that. And of course, you can print that to see, which will be 0.2. So I expect 0.2 of 510 to be in each category. Then I can replicate that for all the 5 groups. So I use the rep function. We've talked about rep function in our previous class. So to repeat, and then we can bind my table and the proportion. And that will give you a new table if you want to see the table. So this is what we now call the theoretical probabilities. The theoretical probabilities. So the issue is whether what we observe agree with this distribution. And that's what the chi-square will test. And if they agree, then we say there is goodness of fit. If not, there is no goodness of fit. So we run, and this is chi-square test for giving probabilities. So we have this is the chi-square value, and this is the degree of freedom 4 because we have 5 groups. So we have 5 minus 1, and this is the p-value. This is very, very small. This is very, very, very small. And so the null is actually saying goodness of fit, and then the alternative is saying the data does not agree with the theoretical probability. So in this case, the test is very, very significant. So which means we are rejecting the null hypothesis. We are rejecting the null hypothesis of goodness of fit. So that is the conclusion, and that's how to test for goodness of fit. If we now, as you will see shortly, we can choose our own proportion that we feel. We might feel that in that population, rather than 0.2 for all of them, we can assign different proportions that we expect and test. We will do that. But there are other things we could get if we so wish. We can get the expected values if we want, which I talked about previously. So this is the observed. If we want the expected, we can also get it. So to get the expected, we can run this line 133 to get the expected. So these are the expected 102 that I talk about. So those are the expected. But the ones you have, these are the observed. So you observed 102, but the expected value is, sorry, you observed 113 when the expected is 102. So same for the rest. And then you can also get the residual. Of course, the residual is the difference between the observed and the observed and the expected. So which is the residual. So we can run this to get this is the residual. By the residual is the residual values, and this you can also get the standardized values or the standardized residuals. I'm just doing all of this. The result you need is actually this one for you to draw your conclusion. But in case you want to get some other things, then you can get the expected value. You can also get the residual values and the standardized residual values. So to get the standardized, this is the command. You just put $standardized residual, STDRS. That is that. So these are the standardized residual. Just like when you talk about standardized value. So the standardized residual has a mean of 0 and a standard deviation of 1. So these are just results that come out of this result. Though they are not reported, but you can call for them. And that's what I've just called for. But in terms of the overall, this is what you need. Now, suppose the test we have done here considers equal probability. We consider, we are testing whether the distribution of education level is the same in terms of proportion for all the 5 categories. But that should not be expected. So we can have another assumption in which we expect 30% of car owners to have completed college degree, 30% not to complete high school, 20% to complete high school degree, 10% to have post undergraduate degree, and 10. So we can test this assumption. So we will now check, does our data agree with this postulation? Does the sample data from this 510 agree with this postulation? So you can run that test also. And again, you can see our p-value is this, which is very small compared to, again, we are rejecting that that postulation. So our data does not agree with this postulation. So this is how if we want to see the expected, what this one is actually saying. It's saying that we are expecting 153 for college degree, whereas what we actually observed was 113. In the other one, is expecting 102, whereas what we observed was 132, and so on like that. Where we observed some college degree, where we postulated 51, we actually observed some college degree to be 113. So this does not agree with. So again, here we reject the null hypothesis. We reject the null hypothesis of goodness of fit. So now, just a caveat. Sometimes if the expected count, just like we have 153, 102, 51, if the expected count is lower than 5, for whatever reason or reasons, then the chi-square test we are using is no longer exact. That's the right word. The chi-square test is no longer exact. So if it's not exact, the alternative is to use a simulated p-value for us to arrive at a decision. And how do we do that? We simply put the simulate.p.value argument to be true. So I run this. This is now run. So I have this. So again, this is this, despite simulating p-value based on 2,000 replicates, yet the p-value, the decision has not changed. Doesn't change the decision. So that's about testing for goodness of fit. And the last thing we will do now, our time is exactly 11, maybe for the next 5 minutes. Let's look at this data, read breakfast data. So what we want to do is to look at, let's look at the data. So this is the data. It's about hotel data collected in hotel. People will the guests in the hotel. So this is the age category, and this is their choice of breakfast. So it's discovered that the first person here is under 31, but the choice of breakfast is cereal. This second person is between 46 and 60. The choice of breakfast is breakfast bar. This is over 60. So age category, this is qualitative. Breakfast is also qualitative. The question is that, is there a relationship between age category and choice of breakfast? Is there any relationship? Is the choice of breakfast dependent or not dependent on age category? So is it that younger people will prefer certain type of breakfast? So if we are now testing for association between two qualitative variables or testing for independence of two qualitative variables, that's when we now use the chi-square test for association. So in this case, we are testing for variable age category and breakfast, whether they are associated. We need this package, which is G models. If you don't have it, you install it. So this is loading, it's loaded. And then I will use the function cross table. And the cross table gives, there are a number of arguments there. This is the first variable, age category. Second, breakfast. Do I want the expected? Yes, I set it to be true. Do I want the proportion of the row? Yes. Do I want the proportion of the column? I set it to be true. Do I want the proportion of the total? Yes. Do I want the proportion of the chi-square? I set it to be true. So you can set it to be false. No, anyone you don't want. But for this one, I set all to be true. So I can run this. It's going to give me something like this. Very big table, but very interesting table. So this is the cell content. The first thing you see there is N, which is the number of counts in that cell. The next is the expected, and I've told you how we obtain the expected. The next is the chi-square contribution, and then this is the proportion, number of the total number of counts in that cell divided by the row total. Next is the, so how do you use this key? If you now go to this table, this is the total observation, which is 880. Of course, that's what you see here. That's what you see here, 880. So the first thing here is 90. And this represents the number of those between the age of 31 and 42 who took breakfast bar choice. This represents those in the age bracket 31 and 42, 45 who took cereal. And this is 24 represents people in age 31 and 45 who took oatmeal. Altogether, there are 206 people or guests in this age bracket 31 and 45. So what you see here, according to this key, is the expected number. Is the expected number. So we expected 54, but we observed 90. We expected 54 people in this age bracket to choose breakfast bar. We expected 79 to choose cereal. We expected 72 to choose oatmeal. But these are observed cases. So then you have the next, which is the chi-square contribution. So this is the chi-square contribution in this case is 23. Here is 2. Here is this. Then of course, the next one is n divided by row total, which is this is the row total. So this is 90 divided by 206. That's what gives you this. And then the next one is n divided by column total. So this is 90 divided by the column total is 231. And finally, the last is n divided by table total. Of course, this is the table total. So which means this is 90 divided by 880. So I leave you to interpret the rest of the table. But the final thing is this p-value, which is also very, 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 very small. So what are we testing? We are testing whether there is association between age category and breakfast choice. So the null hypothesis is saying there is no association. The alternative is saying there is association. So, of course, when there is no association, it means they are dependent. And when there is association, it means, when there is no association, it means they are independent. It means they are independent. And when there is association, it means they are dependent. It means they are dependent. So in our case, so the null hypothesis is saying no association. But here, this is our p-value. So, and it's very, very small. This is about 0.00000. So we are going to reject the null hypothesis, which means this test is significant. So, which means there's actual association. There's association, which means breakfast choice depends on age category. Breakfast choice depends on age category. So they are dependent. They are not independent. So that's what the test has shown. But there is a test, simple test, which helps us to know the degree of this association. Just like in numeric data, when we use Spearman correlation or Kaplan moment correlation coefficient, we can also use what we call Cramer's V test to now determine what is the degree of this relationship. So I will need this package, LSR. If you don't have it, you have to install it, and then I can run it. So the degree of relationship is 0.41. Actually, the value, the measure lies between 0 and +1. So this is, say, it's about 0.4192365. So this is the degree of relationship, the degree of association between the two. Thank you.
Thank you, sir.
Yes, sir. Thanks so much. The class is so interesting and I'm very grateful. My question is, in the alpha value that is usually stated at 5%, 95% confidence interval, as you said. At times I used to see 1% and 10% at times. And I want to ask, can we determine the alpha value by ourselves other than that 95 alone to be that of 99 and 90? And also another question is, can't it go beyond that 10%? Can we have 15% or 20% in some cases, or usually fixed at maximum of 10?
Okay. Now you need to understand what that alpha value, what it means. And I mentioned it. It is the probability that you will reject a correct hypothesis. And nobody wants to reject a correct hypothesis. You want the probability that you will reject a correct hypothesis to be very small. So if you are dealing with medical study, you won't even want that probability to be up to 5%. You want that probability to be as small as 0.00000 because human life is involved, that maybe you are testing a new drug. And so you have no liberty to continue to bring down that that alpha value. You want to make it as small as possible. And that's why in terms of convention, if you are dealing with social science, you are in social sciences like sociology, geography, Greek, and things like that, yeah, you might be okay, that, okay, I can afford to reject a correct hypothesis at well, risk of 5%. I can take I can take the risk of 5%. But do you want to take the risk of 50%, 30%, 20%? No. So that is the consideration. So of course you can, if it's in medical sciences, you don't want to come so low to even 0.05. You want to be 99, if possible, 99.9% confidence that you are taking the correct decision. Do I help you out?
Exactly. It's very clear. I understand. It's clear. Thank you, sir.
You are welcome.